Hello. In this video, we'll talk about geometric properties of linear transformations. So we start with the following definition. A function t, which is mapping v w, is called a linear transformation between two vector spaces v and w if it preserves both vector addition and scalar multiplication. Which means that if we apply t to the sum of two vectors v1 and v2, then the result will be the sum of their images in the space W. And likewise, for the multiplication with the scalar, if we take a vector v1 and multiply with the scalar and apply t, then the result will be the scalar multiplying the image of the vector v1 in the space W, and this works for all vectors v1 and v2 from the vector space V. Next, we talk about important result for the Euclidean space. So we'll formulate it as a theorem. And the theorem says that a function t, which maps the Euclidean plane R2 onto itself, is a linear transformation if and only if there exists a 2 by 2 matrix A such that if we take the vector v and apply t to that vector, then the result is equal to the product of the matrix A and the vector v, and this holds for any vector v which we pick in the vector space V. In relation to this theorem, we have important definition, which is talking about the matrix A we have in the theorem. So the matrix A defined in the theorem is called the standard matrix for the linear transformation T, and its two columns are given by. So we define the first column as an action of T onto the vector 1, 0, and this is the basis vector in R2. And the second column is obtained if vector 0, 1 is taken, which is the second basis vector in R2, and we apply T to that vector. Next, we will have several examples to illustrate linear transformations. So the linear transformations that reflect vectors about, and we will consider 3 different cases. First, we'll reflect vectors about the x-axis. Second, we reflect them about the y-axis. And in the last case, it will be the line y equals x. So for each of those transformations, we have the matrices defined respectively. For the reflection about the x-axis, the matrix has the following form. For the second case, when we reflect about the y-axis, the matrix is defined as follows. And in the last case, the matrix which defines the reflection about the line y equals x is given in the following form. If we wish to illustrate graphically what happens in all those 3 cases, then first we have the vector which will be reflected about the x-axis. So this is geometrically the reflection. In the second case, we have the vector which will be reflected about the y-axis, and that means that we talk about the projection onto the y-axis. And finally, if we talk about the third example, then we need to consider the line y equals x, which is the bisector of the first quadrant. And then our vector will be reflected about this line. We drop the perpendicular onto the line, and then we have the reflection. Thank you very much for your attention.